Listen-only mode.
Hi everybody, thank you for attending today's webinar focused on cooking, the fourth of our Technology Week webinar, our Technology Webinar Week. I want to remind all attendees that this webinar was primarily designed for the participants of the Efficiency for Access Design Challenge, an initiative of the Efficiency for Access Coalition and Engineers Without Borders UK. If you are not part of the design challenge, it is fine. The webinar is in the question box that you will see in the GoToWebinar window on the right of your screen. And I want to remind everybody that this webinar will be recorded and made available online. So today we'll be listening to three people. So Jessie and Leonard from Bern and John. So Jessie is a design engineer. She is a young professional working at the intersection of engineering and sustainable international development. At Bern Manufacturing, she's worked to scope potential new fuels and design new cook stoves products for East Africa. Before working at Bern, she was working in Zambia for an international development consulting firm leading research and data collection. Leonard has dedicated his career to creating a more sustainable future, focusing on green energy, sustainable development, and social quests. He's worked with leading innovative companies on product development, validation and improvements, production processes and tooling development, as well as product development strategy from startup to industrial production. His project portfolio has included cook stoves, solar heat, and electricity, and he is now head of product innovation at Bern. Finally, John Leary is a researcher working with the Modern Energy Cooking Services Program, so the MEX program, which is a program that aims to enable the 3 billion people who still cook with polluting fuels to transition to cooking with modern energy, in our case, electricity mainly. John's role involves empowering everyday cooks to co-create modern energy cooking services that they aspire to use by exploring both how they currently cook and how they aspire to cook, then developing and trialing innovative solutions. So we're going to start with the presentation from Bern. Jessie, Leonard, the floor is now yours.
Thanks, Theo, for that introduction. And hi, everyone. I'm Jessie. And I'll be talking a little bit about Bern, what we do, and then in a broader way, why clean cooking is important and how you might go about working on this as your design challenge. Next slide. Thanks. So why is clean cooking important? Around much of the developing world, people cook with very outdated technology using very dirty fuels is kind of the essence of this. People often cook indoors, meaning that there are health consequences, and then also can spend quite a bit of money and a large percentage of their income on purchasing cooking fuel and replacing pretty bad cooking technology as well. So the two main reasons why making cooking better is the health benefits and then also the economic benefits for families. In addition to making the cooking process easier, better, having better quality food, that's also in there as well. So indoor air pollution and respiratory diseases are a really big health problem around the world. Primarily caused by inefficient combustion of charcoal and wood and inhaling the smoke that's produced when you do that. In addition, using these fuels has environmental consequences, so can cause deforestation, in addition to pollution of black carbon emissions. Okay, next slide, please. So Bern has been working since 2013 to provide better modern cooking technology for Kenya, East Africa, and other countries around the world. So we have a production factory just outside of Nairobi, Kenya. That's where we're calling in from today. And here we produce 30,000 stoves per month. I'll talk a bit later about what exactly we make here. But basically, we make modern biomass cook stoves. So biomass means charcoal or wood. and they help reduce emissions from burning these fuels. They lower the cost that cooks and families have to pay to cook with these fuels, and they help people just have better cooking products and a better cooking experience as well.
And another measure how we measure our success is by the amount of trees saved, because now one of our stoves takes about half of the wood or charcoal that a traditional stove would take. Therefore, we're effectively saving trees, and those will absorb carbon again. So in that sense, it's kind of a double win.
Right. Clean cooking is a really comprehensive issue. It affects a lot of different problems and challenges for people up to entire ecosystems as well. Okay, so we'll start with a poll question. I think Amanda is going to run this. So we'll start by asking everyone who's attending the webinar, what fuel do you typically cook with in your home? So we've provided 4 options here. We were only allowed to provide 4, but these are obviously not an exclusive list of cooking fuels.
So what fuel are you cooking with?
I cook with gas at home, actually. Cool. Yeah, so that's about what I expected. Electricity and gas are considered clean, more modern fuels. Charcoal and wood are more difficult to cook with, are dirtier, and are actually can be much more expensive when purchased in small quantities and have kind of negative environmental consequences. So go to the next slide. Right, so on the left, you'll see kind of the typical options. In Kenya, most people cook with charcoal and wood, usually actually a combination together, depending on what they're cooking. Gas is fairly popular as well, but the traditional stoves are on the left. So the Kenya ceramic jiko is at the top, KCJ, and then a 3-stone fire is the most basic option for cooking with wood. There are also some other basic wood fuels. And then on the right are examples of the improved cook stoves that Burn makes. So on the top are our charcoal cook stoves, jiko koa. So jiko means stove in Swahili, and okoa means to save. So it's a saving stove. And it's more efficient. It can reduce charcoal spending and charcoal consumption by up to 40 or 50% for a household in Kenya, which means that they can save over $2 per week and $119 per year throughout the lifetime of the stove, which is about a month of income every year, and is a really high return on investment from using this stove. The reason why it's more efficient is basically the design of the stove. So one of the benefits of switching from the KCJ on the left to a jiko koa on the right is that it requires almost no behavior change. They both operate the same way. You put charcoal into the combustion chamber, which is the ceramic bowl on the left, and then it's a metal combustion chamber for jiko koa. And then you light the charcoal, usually from below, or you can use some sort of lighting assistant. And then the jiko koa has high temperature insulation that helps keep heat inside the stove and maximizes heat transfer. It has an ash tray that's used for airflow adjustment as well as ash removal. And then the materials used for the combustion chamber and other parts are high temperature alloys. Basically, all of this combines together to burn the charcoal more efficiently. That's where most of the efficiency gains come from, is kind of temperature optimization of how the charcoal is burned. And then optimizing airflow and heat transfer as well. It's a bit technical, sorry. Oh, sorry. Just one comment on the kunio koa is on the bottom. So that's also an efficient wood burning stove. So that also optimizes air transfer, has high temperature metals as well, and that can reduce carbon emissions by up to 80% and use half of the firewood compared to a 3-stone fire. So all of this to say that Burn has produced some technical innovations in terms of how to burn biomass fuels. There are plenty of other ways as well to burn biomass in a more efficient way. The typical options on the left are not really optimized or designed well at all, and yet they're what most people use to cook.
So what may be interesting for you is like how we actually come to a product. So we have a full product development team. I think we're, yeah, depending on how many projects we're running, we're between 5 and 10 people. We work closely together with market research, and so we follow a kind of a typical design cycle from in the sense of human-centered design, where we are looking at the customer first. So we want to really see how are they using their stoves, how much behavior change is acceptable, and what would really improve their behavior or their lives. So we really go to the field. We spend a lot of time with the people that we're developing the stoves for, and see what can make the best impact for them. From there on, we're kind of deriving our design parameters, bordering out how far we can go to one side, how far we can go to the other side. Make sure that we are very sure that we're designing the right thing. So then we get ideas on how we can actually solve those problems that we have posed and that we have found in the first place, how we can come up with ideas that solve them, taking into account all of those requirements that we have stated in the second phase. So they might be on cost, they might be on lifetime, they might be on durability, they are on how many emissions can we actually, or do we want to produce, or how much do we want to reduce it, and so on. So we're trying to get those ideas, select which ones work best, and we build prototypes to validate that actually our assumptions and our ideas work as we have tried to, and then we iterate that. And sometimes you need to go through quite a length to make iterations, because the first idea that you got seems to work reasonably well but not good enough, and then you improve it and you improve it and you improve it. So we're working with modern CAD software to actually draw those things up. We have a really advanced prototyping workshop here where we laser out our parts, weld them together, so that we can get prototypes that are really realistic. So yeah, they're as close to what they will become in the end as possible. And then we have a testing lab where we extensively test those products, not only for efficiencies and power. Maybe we can go to the next slide. So we not only for the efficiency and firepower, but also all kinds of other parameters, like how much fuel did you use to actually heat this water or burn the food that you wanted to make. And so there's a few standard procedures on how to do that, and they are standardized, so therefore we can compare different prototypes and different stoves with each other. But it's always about 5 liters of water in a standardized pot, so that you can create the same testing procedures. So once you're considering to go into developing cooking appliances, then yeah, you have to look at those standardized testing procedures, that you are sure that the measurements that you are making with your concepts, with your prototypes, are comparable to others. Yeah, so obviously we test all the temperatures, because outside you want the stove to be as cold as possible so that people don't burn their hands. But obviously inside you want it to be as hot as possible. And yeah, there's always downsides to every design decision, so you need to balance between the ups and downs. But the key parameters where we're looking at is mainly the firepower and the time to boil, and derive there from the efficiency. And the efficiency is basically you take the energy that's contained in your fuel and how much of that is transferred to the water or other thing that you're cooking. So that's really one of the key things. And then obviously you would want to measure the CO emissions, the carbon monoxide emissions, because those are really detrimental for health, and particulate matter, because that's the thing that gets you lung cancer and other things. Next slide, please. So on side of our lab, we have a durability program where we treat our stoves really badly. We run them for 24/7. So we simulate how a really fast lifetime of the stove would be. So within a few months, we can actually simulate a full lifetime of 2, 3, 4 years of a stove. And we can see what are the failure modes. So we can accelerate what goes wrong and see what we need to still improve. So all of the prototypes that we find good enough in performance, we will place them into this program and run them until they fall apart. And then we see where there are still issues and where we need to improve. Next slide, please.
Cool. So outside of the lab, we do extensive user testing for every product, but especially for something like cook stoves. The results that you get in someone's kitchen or someone's home are often very different than what you would get just based on lab results. So we make sure to incorporate these early in the process. So the main kind of user testing that we do are focus groups where people will come in and actually cook meals on different stoves right after each other. That's a really great way to get a lot of user feedback on what kinds of stoves they like. It's a really obvious way to see what's a benefit or a drawback of a certain stove or a certain fuel. Controlled cooking tests are also helpful. So that's where we kind of measure exactly what ingredients are going into each stove, and that gives you kind of the cost to cook. So on the right, this is based on Burns data from controlled cooking tests on githeri, which is a pretty common Kenyan long boiling meal, a mixture of maize. And so you can see that you can kind of directly compare what it's like or how much it costs to cook on different stoves and different fuels. There's other parameters as well. We usually get user feedback from those sessions. And then home placements are always key because people cook very differently when you're standing there watching them than they do when they're at home not being observed. So we talk to a lot of cooks about how they actually cook in their homes, and then also sometimes try to collect objective data. The stove use monitoring systems or SUMS is an industry standard term that means kind of data collection devices, usually temperature sensors that are placed on stoves in people's homes that tell you how often they're being used and which stoves are being used more than others. And so if you do this design challenge, if you look at cooking, thinking through what it actually looks like for someone to use that stove to cook. So how much does it cost? Do they like it? What are the challenge points? And then even if people say that they like it, how much will they actually use it when they're in their homes? Next slide, please. Okay, so another poll question. How many different types of cooking appliances do you have in your home? 1, 2, 3, and then 4 is 4 or more. Okay, so we have some 2s, 3s, and 4s, but this is actually great because everyone listening today cooks with more than one appliance, which is kind of a key point to make, that a cooking decision is not usually as simple as just buying one stove to cook with. People around the world use combinations. So you'll use an electric kettle to heat up water, you'll use a gas stove for certain types of cooking, maybe a charcoal stove outside. Electricity can be a good cooking fuel as well. So yeah, that's just a point that we wanted to make, because I think often conversations about cooking focus on like the one stove product that people will buy, and that's not really realistic. So leading into, now we'll talk about market research for cook stove development. So this could be its own webinar in and of itself, but I'll go into it at a really high level. These are some examples of different customer segments that we've identified, because each customer segment makes decisions about how to cook and why they would cook with a certain product in a different way. So for example, you have what's called Bora Uhai here in Kenya. They are extremely cost constrained. Cost decision for cooking fuels in the moment, even if it means that over the long term they're spending more because they're spending slightly more per day. You can contrast to all the way on the right, you know, a more cost-focused consumer that's trying to optimize purchases. So they would like to save the most in the long run, which means that they will, if motivated, you know, invest more in a cooking device earlier if it saves them more fuel in the long term. And then these are just a few other examples of other reasons why people might make cooking decisions. Next slide. Right, so then what we like to call them customer journeys. So since cooking is you know, a process that people do 3 times a day and it's really close to their heart, it's something that people are always thinking about. So over the course of their lifetime, people will, you know, everyone will purchase additional products. And so often what we see in Kenya is that people will start with firewood or paraffin. Paraffin is another word for kerosene. Then they might move up to a KCJ, the traditional charcoal stove that we talked about earlier. And then maybe they might move to an improved cook stove plus another fuel. And so almost all customers, like we just talked about, participate in fuel stacking. So these stories are not always linear. People will still have old stoves that they'll use occasionally, and will kind of switch back and forth. Oh, next slide, please. Okay, yeah, so just to conclude, cooking is a really complex issue. The behavior that's involved is, you know, involves like a lot of different factors, people's taste preferences, what they grew up eating, how they grew up cooking, in addition to just, you know, what foods are common in different countries, and what fuel they're using. The products themselves are really small, but are also a very complex system. And so, you know, design decisions for these involve a lot of trade-offs. And there are just so many areas of innovation in this space. So, you know, technology, obviously, designing new products, looking at financial innovation. So how do people spend money on cooking, and how can you get different business models in play for cooking technology? I think there's innovation with traditional fuels because people will probably still cook with these. So how can you make that really, you know, a better experience, and better for the environment and for their health and for the, you know, economics associated with that. And then also there are a lot of new clean fuels, and there's so much room for new technology there and behavior change, which is what I believe John is going to talk about next. And if anyone has more questions about burn, or this, what we talked about, some contact information is on that slide.
Thank you very much for your insightful presentation. We're now going to hear from John about consumer habits more. I do want to remind our attendees that if you have any question, please ask them throughout the webinar so we can address them at the end during the Q&A session in the question box. Thank you.
Hello, can everyone hear me okay?
Yes, we can.
Okay, great. Well, firstly, thank you to Theo and Amanda for the invitation to share what we're doing with you today. And then also thank you to Jesse and Leonard for the excellent presentation, which flows very smoothly into what I'd like to share with you today, which is the opportunity for transitioning to electricity for cooking. Next slide, please. Okay, so my name's John Leary. I'm a researcher currently with Loughborough University. I studied mechanical engineering at the University of Sheffield and did a PhD which started off as engineering, but drifted very much more into the social sciences, as I realized that if you're designing technology for people, you really have to have a thorough understanding of what people want and what people need. And that really resonated with what Jesse and Leonard presented in terms of their product development process, in that you have to start with the user and then really understand how they work before you go about thinking about how a machine that might be able to help transform their lives might work. So I did quite a bit of work with Engineers Without Borders, including what's pictured in this photo here. This is me in rural Guatemala with a pedal-powered water pump that I designed during my master's project. At the time, there wasn't anything like this kind of design challenge available. So this is a really great opportunity and something I wish I had the opportunity to participate in the time that I was studying. So please do make the most of it. I'm now at Loughborough University and I'm working on electric cooking, specifically on the Modern Energy Cooking Services program. Can we go on to the next slide and I can talk a bit more about what that is? So Modern Energy Cooking Services is a UK government-funded research program designed to find pathways to enable the 3 billion people who are currently still cooking on biomass to transition to modern energy for cooking. So as Jesse, I think, was emphasizing before, what we mean by modern is electricity or gas or potentially some other fuels which really are clean in terms of the health impacts of using them, and have a user experience which is much more easier to use, for lack of a better word, than charcoal or other solid fuels, which really require a lot of time and a lot of skill from the cook. So I'd like to start with understanding the cook and present a couple of methodologies that we use to try and understand how people in sub-Saharan Africa and South and Southeast Asia currently cook, and how they aspire to cook in the future. I would like to share with you what we found out about the menu specifically in urban Kenya today, and then present a couple of opportunities. As you'll see in this picture here, there's an electric pressure cooker, and there's also a battery next to it. So when I was studying mechanical engineering at Sheffield and working with Engineers Without Borders, then we were always used the kind of unwritten rule that you really shouldn't do anything to do with heat on batteries, because it's a waste of high quality energy, turning it into low grade heat. But really the world is changing, and I want to draw your attention to an opportunity, an emerging opportunity, to use battery supported electricity to bring access to modern energy cooking to billions of people. Next slide, please. Oh, sorry, I forgot the last point on that slide is why it's relevant to you, which is I want to end with some ideas for where you could focus on your design challenge, where this opportunity needs to go next in order to have the biggest impact. So I'm not going to spend too long on the problem of clean cooking, because I think Jesse and Leonard did a fantastic job of outlining that already. I just want to say that in terms of high-level political goals, then the global community has decided that the whole world should have access to energy in order to be able to develop to its full potential. And that the way that is divided currently under the Sustainable Development Goals, specifically goal number 7, is to say, well, people need access to electricity, but they also need access to clean cooking facilities. So the two are completely divided at this stage. You have the electrification industry, which has seen rapid progress, with many people being connected to grid electricity and many off-grid solutions such as solar home systems and mini grids being disseminated at scale across the world. Whereas in clean cooking, in general, there's been quite slow progress, and in some contexts, particularly in sub-Saharan African nations, that progress has actually been negative, as in population growth is going faster than the number of people gaining access to clean cooking. And there's been a focus historically on improving the efficiency of biomass cooking. So that is improving, as we heard from Jesse and Leonard, the efficiency of getting that energy, which is chemically embedded within the fuel, into heat in your pot, which will cook the food. As a result, electricity has traditionally been discounted by the clean cooking industry because of a range of problems. Many people not having access to electricity fundamentally. If you live in an African village that's not connected to the grid, until recently, it's just not even on your radar at all. Poor quality wiring, blackouts, low voltage, and also cultural considerations. But the world is changing. Can we go on to the next slide, please? And there are emerging opportunities, such as, for example, the opportunity to cook on solar home systems. So we've noticed that solar panels, and in particular lithium-ion batteries, have been coming down in price quite rapidly over the last decade and back, but particularly most recently in this last 10 years or so. And at the same time, then the price of charcoal in many contexts where they are heavily deforested and there's very few trees left is rising quite rapidly. This means that the costs of alternatives, in particular cooking on a solar home system, start to get to a tipping point whereby the costs, the discounted costs, discounted as in if you break up that big costs of the solar home system into small manageable chunks that someone could repay over time, are getting to a point where they are on a par with what people are currently paying for biomass fuels. Next slide, please. So battery-supported electric cooking can enable you to take electricity from any kind of source which produces electricity on an unreliable basis, for example, the sun, which is only there in the day and when it's not cloudy, or a grid which may have frequent blackouts or very unstable voltage. So you basically store up the power when it's available, and then you discharge the power into your cooking appliance when you want to cook. Next slide, please. This has been made possible because of a shift towards service delivery business models. So in the past, people generally just bought stuff, whereas now, especially in the solar industry, there's a whole financial system that's been set up to allow people to repay the cost of things that are actually quite expensive, like a solar home system, over time in small, manageable repayment systems. And that has worked well for solar lighting products. And the next logical step we see is going up a little in terms of the scale of the size of the system and therefore the cost into the world of solar electric cooking and more broadly battery supported electric cooking on a range of different energy sources. So obviously key to making this affordable is reducing the cost of the most expensive component, and that is the battery. So you can optimize the size of that battery by carefully considering what do people want that electricity for, and which appliances can they use to cook more efficiently, and which practices can they use to cook more efficiently. What do I mean by that? For example, practices, I mean, for example, if you have dried beans, soaking those beans overnight can already reduce the energy demand by half. And going from an electric hot plate to an electric pressure cooker, for example, can reduce the amount of energy you need by up to 80%. So in addition to these price drops of solar panels and lithium-ion batteries, there are now new ultra-efficient electric cooking appliances available. Back in the 1970s and the 80s, the only choice was really an oven and a hot plate, and maybe a few other very specific appliances, kettles, for example. But in the last few decades, then many other new appliances have been developed and are now available on the mass markets. Next slide, please. So what we want to find is what is the LED of battery-supported electric cooking. So the LED has really been one of the key catalyzing factors in the transition to solar electric lighting across the global south. So particularly in sub-Saharan Africa, using incandescent light bulbs requires you to have a solar home system sized about 10 times as big as if you're using LEDs. So the development of cost-effective and reliable LEDs allowed people to gain access to affordable lighting, because not because the LED was that much cheaper, but because the battery and the solar panel required to power that LED was much smaller and therefore much cheaper. So there's a whole range of electric cooking appliances available on the market today, some that are even not appliances, for example, just putting a lid on your pan, behavior change. But which one of those can give us the greatest amount of impact in terms of reduction of energy demand? Next slide, please. Okay, poll. So can I ask, how often do you cook at home? Do you cook all the time? Apart from occasionally maybe when you go out for food? Do you cook often? Do you cook rarely or never? Okay, fantastic. So already the vast majority of people either always cook or often cook. So actually you've already gone on to the first step of the product design process, which is understanding the user. And that's one of the things that I really enjoy about working in the clean cooking industry, because it's something that many people do at home, and it's something that I personally enjoy, and I personally enjoy taking home the gadgets that we build and testing them whilst I make dinner. I find it's an experience that really helps me to understand the perspective of the user and helps me to design products that are much more tailored to real needs and aspirations. Of course, it's still essential to understand the needs of cooks in different places, which is why we designed a study called the Cooking Diary Study, which I'll come back to later, because my needs as a cook are not necessarily the same as the needs of a cook in a village in sub-Saharan Africa. Okay, so of all of these appliances, we started by thinking, what are the benefits and what are the drawbacks? So drawbacks, we've got phrased as behavioral change barriers. So if you're given this appliance for the first time, then what is going to stop you from using it to do all your cooking? I mean, quite fundamentally with some of these, like for example, a kettle, it's really only designed for water boiling. Maybe you could get away with making soup in it, but it'd probably be quite messy and you probably wouldn't want to use it for water boiling afterwards. Things like the microwave and the electric pressure cooker, many people are put off by the complicated buttons that you have on the front and the fact that you can't stir the pot whilst it's cooking. In contrast, things like, for example, the hot plate or the induction stove, you can put any kind of pot on it, but you're still losing quite a lot of heat out of that pot. The induction stove in particular, then you have to have certain types of pots. You can only use steel pots, which is quite frustrating, especially as most sub-Saharan African households that we've worked with tend to have aluminium pots. Next slide, please. But also there are drivers that mean that once people start using these, they want to keep using them. So, for example, for the electric pressure cooker, it really speeds up long cooking foods. And I know from myself cooking in the UK, I don't really cook that many long cooking foods. For example, if I'm going to cook beans, I just buy a can and I essentially just warm them up. But in many sub-Saharan African contexts, people are cooking more raw foods. So, for example, beans may be dried in the farm and they have to be rehydrated or cooked for a very long time. In which case, having a cooker that cooks long boiling dishes starts to become very important. Next slide, please. So what I wanted to say with this is that whilst the focus historically of the clean cooking industry has been on improving the efficiency of this bottom bit in orange, which is getting the heat into the pot, there's been very little attention paid to all of the other means of inefficiencies in the cooking process. So actually there's evaporation from steam, there's convection coming out the side of the pot, there's convection coming and radiant losses coming from the lid of the pot as well. And many of these, there's not that much you can do if you have an open flame underneath, because if you put any kind of insulation around it, then it'll probably catch fire or put your flame out. Next slide, please. So one thing that electricity allows you to do that you can't do on any other fuel is to insulate not only the pot, but also the element inside. So the element is inside the insulation. And that really means that you have much more effective means of keeping the heat that you put in there in the pot, rather than letting it go away into the air, which in, for example, a UK or a northern context in general is useful if your house is cold and needs heating anyway. But in many sub-Saharan African contexts, it's already quite hot, and heating the cook further is not desirable. Next slide, please. Next slide, please. Thank you. Okay, so the electric pressure cooker I've been going on about quite a bit, but what actually is it? Well, it is a combination of familiar things. It's simply an insulated box with an electric hot plate inside and a pressurizing chamber, plus a fully automated control system to essentially do all the cooking for you. Really, all you have to do is put your food inside with the right amount of water and then turn the timer to the right amount of time, and it'll do everything else for you. Next slide, please. So I'd like to ask, how many people have used an electric pressure cooker or EPC before? Do you have one? And if you do you use it regularly? If you have one, is it one of these things that sits in the cupboard and maybe once a year or so you get it out for its annual cooking session and blow off the dust? Have you maybe heard of them, or possibly you tried one out at someone's house but you don't have one yourself? Or have you never heard of them before? Okay, so most people have heard of them, but not used one. This is a similar situation to me when I started doing this kind of research about 3 years ago. I had kind of loosely heard of them, but I had never used one myself. And really, for me personally, it's revolutionized my cooking. I now do the majority of my cooking in an electric pressure cooker because it saves me a lot of time, not just the time in terms of cooking the food, but also being able to leave it to go and do its thing whilst I go off and do other stuff like a webinar or write a paper or go out and enjoy the nice weather, any of these things. It stops you having to sit there and babysit the pot, which can be fun sometimes, but is a chore. Next slide, please. Thank you. So the cooking diary study, we asked 80 households, back one please, thank you. We asked 80 households in 4 different countries, Kenya, Tanzania, Zambia, and Myanmar, to spend 6 weeks recording what they cooked, how they cooked it, and how much energy they used. For 2 weeks, just cooking how they were cooking before, just recording, and 4 weeks trying out electric cooking. A range of different appliances, including the electric pressure cooker. Next slide, please. What we found was that of the appliances that people had available in Kenya, for example, they had each household had a hot plate, a rice cooker, and an electric pressure cooker. And both charcoal stoves and the electric pressure cooker are heavily favored for what we call heavy foods. So heavy foods are the things that take a long time to cook. Things like your beans, which you would boil for hours. They're the biggest energy consumers, and they're the ones that if someone has a gas stove, then often they would still buy charcoal to cook because they think it's cheaper to do so. One of the key findings of our research in the cooking diaries was that actually, despite the perception that electricity is expensive for cooking, it's actually far cheaper than charcoal. So this is based upon grid-connected electric cooking in Nairobi using current prices, which are similar to prices in the UK. And the cost of cooking beans on charcoal is around 80 shillings. So that's around, in US dollar cents, around 80 US dollar cents. And the cost of doing it on an electric pressure cooker is around 11. So it's an order of magnitude cheaper. It's not just a little bit cheaper, it's a lot cheaper for heavy foods. Okay, next question, or next slide, please. But how often do people cook heavy foods? Well, we know from the diaries what they cook and when. And we know that heavy foods make up about 1/3 of the menu. So what about the other foods in there? You've got staples like ugali, some maize meal porridge that you have to stir, rice. You've got things that you have to fry quickly, like eggs, for example, things that you have to deep fry, and things you have to fry for a long time with a shallow pan. So actually the last two, they don't make up a significant portion of the menu. So perhaps they're not that important, but the staples and the quick fry make up a bigger portion than the heavy foods. So there's a key kind of enabler here for these technologies. If we can persuade people that either they can cook using these appliances, they can cook using they can cook staples and quick fry foods using an EPC currently how they already are, then they can do more of their cooking on an efficient electric appliance. Or if we can modify the design of electric pressure cookers to better cater for these foods, then again, we can shift more of the urban Kenyan menu into efficient electric devices. Next slide, please. So how could we do this? For example, for the staples and the quick fry foods, simply demonstrating to people how easy it is to cook those foods, in many cases seems to be enough. Showing people that actually ugali, a major staple across East Africa, is actually very easy to cook in an electric pressure cooker, seems to persuade many people that they also can cook their ugali in it. Possibly having another electric pressure cooker, because many people report that actually the reason why they use another stove is just because they want to cook two things at the same time. For the quick frying things, then there are issues around the pan itself. An electric pressure cooker only comes with one pot and is a very deep-sided one. If you want to cook an egg, for example, frying an egg is very easy, but getting that egg back out without turning it into mush is quite difficult. The deep fry foods and the long fry foods, I'm not going to focus on them because, again, it's not a huge percentage of the menu in Kenya, at least. In other places, maybe it is. Next slide, please. So ultimately, the reason why we have focused so much on the electric pressure cooker is because we see it as a very energy efficient device and also a very useful one. But key to achieving its potential for transforming lives is getting people to use it for as much of their cooking as possible and to do that cooking efficiently. So having an electric pressure cooker in your kitchen and keeping it in the cupboard, gathering dust, is not the outcome we're looking for. What we're looking for is that people cook as much of their food as possible and save as much energy and therefore time and cost as possible by using it. Next slide, please. So to conclude, then we think that electric pressure cookers, or EPCs, have a huge potential for tackling global health, environmental and gender equity challenges associated with cooking with biomass. However, as key design challenges that you can take on to increase the impact of electric pressure cookers, I'd like to suggest that by integrating batteries or other devices into the electric pressure cooker itself, you can enable access to those who don't have a strong grid connection or who live in off-grid regions where there is no grid connection at all. We can lower behavioral change barriers and amplify the drivers. So the barriers, for example, not being able to look inside the pot, and the drivers, the fast cooking. How can you emphasize that? How can you make the positives more positive, and how can you mitigate the negatives? And finally, cooking a broader range of foods. As I went through on the menu, then you see in Kenya at least, they're absolutely amazing at 1/3 of the menu, and they're kind of okay and get used occasionally for the rest of it. So how can we encourage people to take on the rest of their menu? How can we, sorry, distracted by an alarm there. How can we encourage people to do as much of their cooking as possible in an electric pressure cooker and save as much energy, time and money as possible? That's the end. On the next slide, then there is some contact information. where there is a link to a website which actually has quite a few more resources on there, mex.org.uk. So if you look on there, have an explore around, there's a whole bunch of different reports, videos, briefs, and most importantly, the e-cookbook that we put together for cooking heavy foods in Kenya. So please do go and have an explore, and don't hesitate to get in touch with me on that email address if you have any questions. Thanks for listening.
Thank you very much, John. That was very insightful. We're going to now move to the Q&A session. So we have a few minutes. Do feel free to keep asking questions in the meantime. I'd like to start with a question for Bern, but John, I'm sure you will have things to add to the answer. You mentioned that the first step in any prototyping process was to do a market research. Could you be a bit more specific on what you're looking at in this market research when it comes to cooking?
Yeah, sure. I mean, the quick answer is that it depends on what question you're trying to answer. There are so many different market research tools and ways that you can ask people about cooking behavior that will help you with some questions and not with others. But for example, when we're looking at maybe a new fuel or a new product, first we start by trying to understand all of the behaviors that currently exist with that product. So if you were looking at gas cooking, you might go and talk to people who currently use gas about why they like it, how they use it. You could watch them cook. You can ask them what products they buy, how often they use it, how much they spend. And you can do that, with in-depth interviews. You can also do that on the street with passersby. And that will give you kind of a sense of the, existing products. And then if you're, a bit further in your kind of idea phase, what we often try to do is put together a prototype as quickly as possible that maybe doesn't function in the exact same way as it would in the long term, but then you can take that and, show it to people maybe next to the alternative and say, like, what do you think of this product? How would you use this? And get kind of initial feedback like that. And then as soon as possible, we invite people to cook on any prototypes that we have, because that's the ultimate test.
Great, thanks. John, I don't know if you want to add anything, or we can move to the next question.
Oh, I think that's a very comprehensive description.
Thank you. So we have another question. I think it's more for you, John. The question is, how efficient is it to use an induction stove with a pressure cooker, so a normal pressure cooker, non-electric, on top of an induction stove? And I guess in comparison with other solutions such as an EPC.
Yeah, good question. So many people, when they think of efficient electric cooking, the first thing they think of is induction stove. So yeah, you can go out and you can buy a standard stovetop pressure cooker, or maybe you already have one. And if it has a steel base, then you can put it on the induction stove and you'll get the advantages of efficient heat transfer into the pot, and you'll get the advantages of faster cooking. So you might be able to cut your cooking time in half depending upon what you're cooking in there. What you won't get is the benefits of insulation. So the heat going into the pressure cooker will leave just as easily. And also another difference with stovetop pressure cookers is that they often have steam coming out the top of them, which again is energy that's leaving. Anytime you see steam or you feel heat around the outside, that's an inefficiency. So in terms of how efficient they are versus electric pressure cookers, I'm not sure I can give you a specific figure, as we haven't done that test ourselves. Although having said that, we do have some colleagues in Nepal who are doing that as we speak, but we don't have the data yet. But really, for me, the biggest difference between them is the insulation. I mean, just insulating a pot alone, we had some students at Nottingham University who did an experiment and showed that you could save half the energy for cooking simply by putting insulation around the pot. No pressurization, nothing else.
Great, thanks. Another question is about cultural specificities. So obviously cooking is really tied to each country's habits, as you mentioned, and both of your organizations are working mainly in Kenya. what would it take to adapt an appliance to a different country, and what would be the challenges that are induced by cultural specificities? I don't know who wants to take the question first.
I don't mind taking that first, unless Jesse or Leonard, you've got something on the tip of your tongue.
That's fine, you can go first.
Okay, well, I think that's a really great question, and that is essentially what my job will focus on for the next 4 years. So how you understand a different culture, how they cook, and how compatible different electric or other modern cooking solutions might be is a real problem. Some cultures are very similar. For example, we did the cooking diary study in Tanzania and Zambia as well, and we found that actually the way that people cook is relatively similar. Whereas we also did the study in Myanmar in Southeast Asia, and we found that the way that people cook there is very different. The foods that they cook, the techniques that they use are quite different. So in fact, we don't emphasize the EPC as much when we are working in Myanmar. We look more at rice cookers and electric frying pans. So the way that you can understand how compatible these solutions might be in other places is to try and characterize the cuisine. So what do people cook, and how often do they cook those things? You might say, well, there's this one specific dish that people really like and is really important, but if they only cook it on special occasions, then it shouldn't have a big bearing on what solution you come up for an everyday cooking device. So I'd say if you're thinking of a specific country, maybe start with those categories that I had on the slide about the Kenyan menu, and think, well, how does the regular menu in that particular country pan out in terms of what proportion of dishes do fall into each of those categories? And in fact, in some countries there are other categories as well. Like, for example, we're just about to start working in Morocco, and apparently baking is a big thing there. So it doesn't even feature on the Kenyan menu. So it wasn't even a category listed there. So I'd say think about the food categories and think about the frequency in which they're cooked, and then which appliances cook those categories well.
Great, thanks. Anything to add on Bern's side?
I think that was a pretty good answer. I mean, just to kind of underscore, this is a really important question in cooking and cooking design. So the Jiko Koa came about from research in Kenya, but we actually sell a lot and export our products to Somalia and Tanzania and Uganda and Zambia. So I think there's a variety of foods that people cook in each country. There are kind of larger macro differences, but then there's also, as John I think pointed out on one of his slides, there are certain devices that lend themselves to more flexibility. A charcoal cook stove is one of those. You can put, a wide variety of pots on top and cook a lot of different meals. And then there are some cooking technologies that are a bit more specific. So I think keeping that in mind as well.
Yeah, I think all of these answers, they summarize it pretty well. But there's a lot of factors you can look at. It's like, when are people cooking? Are they cooking daytime or are they cooking nighttime? What are the volumes? Like, are they cooking for a small family of 3, or are they cooking for the whole extended family of 12? So those are really important factors. And I think the only key there is really look at the customers, look at what they're doing, and then see if that solution that you have in mind can fit or not.
Great. Thank you very much for these answers, very insightful answers. I'm sorry we don't have time for more questions, since we're reaching the end of our webinar. So I want to warmly thank our speakers today for their very insightful presentations. Thank you very much. To all our attendees, we will meet again tomorrow at the same time for our last webinar of the week, focused on power management. And we'll hear from Mkopa, from the battery research lead from Mkopa, and from Innovex Uganda, a company working on sensors. Thank you very much to all of you, and have a very good day.
Thank you.
Thanks for having us.
Thanks.